Hello everyone, welcome back to another section. So today we're going to start chapter 11. So 11.1 is Introduction to Trees. All right, so here are a few homework problems you can try, 2, 4, 6, 8, and 10. All right, yeah. So yeah, Introduction to Tree, there you go, that's the tree. Yeah, I'm just kidding, right? So yeah, so we're gonna take a look at the graph, but then in terms of tree, and you can see here, tree, we need to have a root, you have branches, and then you're gonna leaf, things like that, right? So the concept is idea is the same as a tree model. That's why I kind of put this picture here for you guys to see. All right, so all right, so let's take a look at the definition of tree. So what is tree? A tree is a connected, undirected graph with no symbol circuit. Okay, no symbol circuit. So that's how we define tree, right? So remind yourself, a circuit is you start from one point and you go around and you go back to the same points again, right? But now you don't want any symbol circuits on that. So yeah, mean that you can be able to go from one place to another place without using any circuits on that. So take a look at this graph below. So the question is this a tree? Well, again, so is that connected? Mean that can I go from one point to another point? Yeah, absolutely. But again, do I have any circuits involved? So as you can see that we do have one circuit, right? So 3, 8, 7, 10, that's the symbol circuit. It's a symbol circuit. So it's not a tree. Is that good? Yeah. So if you erase this guy right here, then everything's still connected and now it's become a tree. All right, so you can remove that edge and now it's become a tree. But without that removal, we don't have a tree. So that's the idea. So yeah, number one, it must be a connected graph and there's no circuits involved, any circuit at all. Could be length 3, length 4, length 5. As long as you don't have any circuits involved in the graph, then that's graph considered a tree. So yeah. So let's take a look at a few examples here to see whether we can see where which one is a tree. So if you look at part A, right? So is everything connected? Yes, you can go from one point to another point. Is there any symbol circuits? The answer is no, there's no symbol circuits, right? So A is a tree because the graph is connected and no symbol circuit. Okay. How about B? Well, B is not a tree because it is not connected. Right, you can see here B. So those are the gap. So not connected right there. All right. How about C? All right. So are they all connected? Yes. Is there any symbol graph? The answer is no. You see here, this kind of overlapping, but they don't intersect each other, right? Remember planar, right? So how do you know it's intersect each other? It will have to be represented by a dot. So this one here, there's no dot involved. So yeah, they're not intersected. So C is a tree. Okay, because it's all connected and there's no symbol circuits. So that's how you explain, right? Using the definition. D, okay, so D is not connected, as you can see. It's not a tree because there is a symbol circuit. And where is that symbol circuit? Right here. That's a symbol circuit. So therefore, it's not a tree. Is E a tree? Yes. E is a tree. Yeah, everything is connected and there's no symbol circuits. All right, so F a little bit tricky. Is that a tree? The answer is, all right, take a guess. Okay, a bit tricky than the other ones, but again, it's not a tree. A tree, because there is a symbol circuit. Where is that symbol circuit? Right here, right? So you can see here, you can go back to that, and that's a circuit, right? So that's not a tree. All right. So does that make sense? So I just show you 6 examples here to kind of guide more the idea what is a tree and what's not a tree. All right. Now another theorem here. So beside the definitions, so this is alternate form to define tree. So in undirected graph, it's a tree if and only if there is a unit symbol path between any two of its vertices. Okay, a symbol path, not a symbol circuit. Right? So you can pick anything, you can go from there. For example, I want to pick this guy, all right? I want to pick this guy and this guy. Can I go there? Yes, I can go there, right? So pick any vertices. Can you find a path from one to another? Then if you can, then that's a tree, okay? No symbol circuit. All right, make sense? Yeah, that's how we define tree. Very easy, right? Yeah. Now, as I said, in the first pictures that you saw, a tree needs to have a root, okay? So how do we define a rooted tree? So a rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. So you look at the tree, right? You only have one root and then it's grow up and then it's branched out, right? So there's like 2 root, 3 root, right? There's 1 root, but then you might have many branches. The idea is the same thing, right? You can pick one vertex as a designated root and everything else have to be directed away from the root. Make sense? Again, we know that graph have many presentations. So, you know, you might have this look like this look like that, but it's all part of the whole graph. And if that graph is a special graph, it's considered a tree. All right. So suppose we have this graph right here. Okay. So I know that A will be the root here, right? So G cannot be a root, F cannot be a root. A has to be a root because you have to have a designated vertex. And that designated vertex will always be your root, right? So this is the case. So this guy here, A, is the root of the tree. All right? Everything's directed away from the root. Make sense? Okay. So here is a graph, a T, right? So it's just a regular graph. But now we're gonna make a tree, and then I'm gonna show you 2 different roots. So you can see it's a same connected graph, but presenting differently, right? Depending on how the question asks. So the first one said, okay, so now the question wants us to say, I want A to be the root for the whole graph. So where's A? So A is the root of the whole thing. So that will always the starting point, right? So you gotta always put it on top. So A will be on top there. And now you see A is connected to D, A is connected to B, and then A is connected to E, to C. So those should be the same level. You can see here, B, C, D, they should be in the same level. Yes, because those are the 3 neighbor of A. So they need to be the same level. And then you're moving on. Okay, so B, all right, so B now reached out to F and G. When you look at this graph, B now reached out to F and G. And D doesn't reach out to anything, so it's end up right there. And C reached out to E, so C reached out to E. So you can see here, they all connected particle, but then they present things differently. So that's with root A. Now, if you pick another one to be the root, let's say we pick root C, right? So now you want root C to be the root, and now you look at that C, right? Let me erase the original one so you can see. All right, C. So what's the neighbor of C? C have A and E as neighbors. You can see here, C go to A and C go to E, right? And E stop right there. But now A have D and B as neighbor. So A have B and D as neighbor. So we try to follow, the alphabet order of that, right? So you can see here, right? A, B, C, D, left to right alphabet orders, and then F, G, right? So the neighbor of B are F and G, but F came right before G. So we're gonna use that direction. So alphabet orders when you compare those. All right, so you can see here, A reach out to B and D. So alphabet order, you're gonna write left to right, so B and D. And then D stop right there, and then B reach out to F and G. So there you go, right? So it's the same exactly graph as the graph T, but then when you pick A as the designated root, you have a different graph. When you pick C to be the designated root, you have a different graph, and they all part of a tree. Make sense? There you go. All right. All right, so now a few more definitions. Descending path. Descending path is a unit path from the root to any vertex, right? You start with the root and then descending to any vertex. We call that descending path. And here we define the ancestor and descendant. If there is a descendant path from V1 to V2, then V1 will be the ancestor of V2, and V2 is the descendant of V1, right? So you can think of, relate to us, right? So our grandparents to our parents, parent to us. So, grandparent would be the ancestor of us and so on, because there's a path from grandparents to our parent, and then from parent to us. So that's the idea of that. And we are the descendant of our parents, right? So that's the concept of that. And then further, parent, if V is a vertex other than the root, okay, so the root doesn't consider, so V is a vertex of other than the root. The parent of V is the unique vertex U such that there is a directed edge from U to V. So if there's a directed edge from U to V, then U is the parent of V, and because U is a parent of V, then V is a child of U, right? So between you and your parent, right? So your parent go to you, then you are the child of your parents. That's the idea of that. And then you and your sister, they're considered sibling because they have the same parent, right? So that's the idea of sibling. Same thing with tree, right? Now, a vertex with no children is called a leaf, and the vertex that have children are called the internal vertices. Okay, so that definition very clear. Right, children with no children called a leaf, and would have children we call internal vertices. And if A is a vertex of a tree, then you can always, get a subtree with A as its root, but it's a subgraph of the tree consisting A and all of its descendants. So, think of this, right? So when you have a tree and then you chop down a branch, then technically you take everything from that branch you chop out, right? You can't just take out that branch. So you take all the descendant of that branch too. So that's how we call that a subtree of that, all right? Okay, so here is the example. Suppose we have this graph present to you here. It's a giant graph. All right, so you can see here, A is the one that started first. Right, so A would be the ancestor. Okay. So A will be the root, right? A will be the root, right? So let's put it that way. All right. So find the parent of C. So where is C? So C is right here. What's the parent of C? You can see that C is tracing back to A. So A is the parent of C. So A is the parent of C. The children of G. right? Does G have any children? So G does not have any children. So G does not have any children of any child. All right, what else? The sibling of H. So the sibling of H is on G, right? Because they are the same level here, because they share the same parency. So the sibling of H is G. That's it. That's the only sibling H has. And then the ancestor of E. So the ancestor of E. So E here, so E go back to B, and then B also go back to A. So yeah, so the ancestor of E are B and A, because they are descending path from B to C, and there's also a descending path from A to E, which is A, B, and E. So the ancestor of E are B and A, right? All right, so the descendant of B, all right, so what's the descendant of B? So the descendant of B are E, F, L, M, and N. Okay, because B is the ancestor of E, F, L, M, and N. So therefore, the descendant of B will be E, F, E, L, and N. All right. So number 2. Find all internal vertices and leave. Right. Again, the root does not count as internal vertices. So internal vertices are right. So as long as it have children, it's considered as internal vertices. Right. So B has children. Okay. So B have children, yes. C have children, yes. And D have children, yes. So those are the 3. And then F also have children. And then H also have children. And then what else? J also have children. And then Q also have children. And then T also have children. And then now we look at the leaf. So the leaf are the one that doesn't have children. So E is the leaf. L, M, N as leaf. And then G doesn't have children, so, and then O, P, and then I, K, all right, I, K, O, P, and then R, and then S, and then U, that's a U there. R, S, and U. All right, so those are the leaf of that. Now, does that make sense? All right. So now part 3, the last question. So question is, what is the subtree rooted at D? So where's D? So now you're gonna cut it, right? You're gonna cut it. You're gonna cut that one, right? So you're gonna cut it. So imagine you chop out a branch, and so this will be a brand new subtree. So that will be the subtree rooted at D. Okay, the entire things. Okay, subtree rooted at D, right? You cut out the entire thing. So you have I, J, K, and then Q, R, and S, T, U. All right, makes sense, guys? All right, so that's a little bit of definition that you see. Go through the example that we have. right? So tree can be presented as a lot of models, especially in computer science and chemistry, geology, right, psychology, and many other areas. So you can see here, you take organic chem. So this is the idea of, excuse me, of tree. So you have a butan and you also have isobutan, right? Yeah, all right. So they are the same representation of butans. We call isobutan. So that's a tree. And so tree was introduced by the mathematician Cayley in 1857, right? And his work is amazing, counting the number of isomer of saturated hydrocarbons, right? And on the right-hand side here is one applications. And you know, when you look at your mailbox, yes, so you look at the inbox, you can divide them into a bunch of you know, mail for that, right? So junk mail, and then recycle bin, and then printer and file. So those are the idea of tree, right? You can see that. Okay. Yeah, just like when you create a folder and you create a subfolder and then there's subfolder involved, that's a tree. Yeah, well, a lot of application you can see that in real life that we have. All right. You look at the companies, there's tree too. There's a president and then the VP, and then under VP there's some other, right, people work for that, right? VP of directory, marketing, VP of services, VP of finance, and under that would be, director of accounting, director of miscellaneous, and then a lot of things. So yeah, you can use tree to present a lot of things. And then you look at the your family history, right? That's a tree, right? Start with your ancestor and then go on and on and on. So that's also an example of a tree. Yeah. So now we look at embryo rooted tree. So what's the difference between rooted tree and embryo rooted tree, right? So a rooted tree is called an embryo tree if every internal vertex have no more than m children. So you look at the embryo, three array tree, then every internal vertices cannot have more than 3 children. All right. So a tree is so you could have 2, could have 1, but you cannot have more than 3, right? If you have a 3-array tree. So that's a 3-array tree. So now any tree is called a full embryo tree if every internal vertex have exactly m children. So you cannot have, let's say you consider the 3-array tree, you have to have 3 children for every single internal vertices. Okay. And when you m equal to 2, instead of call 2-array tree, we call that binary tree. And you kind of work more with the binary trees in computer science, right? So here we have a few graphs here, right? T1, T2, T3, T4. It's a graph. We call it tree, so we call T1, T2, T2, T3. So you can see here that it's have this is the internal vertices, right? So you can see here, you can see there, you can see there. They all have 2 children, right? So T1 is a binary tree. You can see here, this guy, internal vertices. They all have 3 children each, yes? So there you go. And then this guy, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is a full five-array tree. This one here, 1, 1, 2, 1, 2, 3, 1, 2, 3, 1, 2. So this is it's not a full embryo tree on itself. And you can see that it's not even an array tree, right? Because you cannot have more than the children they have. So this one here, you can see you have 2 children, but this one happened to have 3. So it's not even defined as an array tree, right? You cannot, right? Every internal vertex have no more than m children, right? All right, sounds good. All right, so there you go. Okay, so let's move on. All right, so now we have ordered rooted tree. So what is that? An ordered rooted tree is a rooted tree where the children of each internal vertex are orders. Okay. So we draw ordered rooted tree so that the children of each internal vertices are shown in an order from left to right. Okay, that's why we have an ordered rooted tree. So a binary tree is an ordered rooted tree where each internal vertex have at most 2 children, right? That's what we call binary. If an internal vertex of binary tree have 2 children, the first children is called the left child, and the second children called the right child. And the rooted tree of the left child of the vertex is called a left subtree, and the tree rooted at the right vertex is called the right subtree of this vertex. All right. So suppose we have this graph. What's are the left child and the right child of D, right? What's the left child of D? The left child of D will be F, and the right child of D will be G, right? And you can see here, right? Okay. And next one, what's the left and right subtree of C? So where's C, right? So the left subtree of C would be H and J, and the right subtree of C would be I, K, L, and M. There you go. Right. So on the left hand side of C and on the right hand side of C, that's the answer for that. Okay. Does that make sense? Okay. So that's the order rooted trees. And you can see here, we still try to use alphabet orders, right? You can see A have B and C, so B and C, B will be on the left hand side, C will be on the right hand side, and B have D and E, so D all will be on the left hand side, and E will be on the right hand side. Okay, so it's not that we try to follow. So we compare one at a time, right? Using alphabet orders. Now we look at the level of vertices and the height of the tree. So you can see here, why don't we write everything in a one choice sentence, but why do we have to break apart? Well, because it's very important which one is a neighbor of which one, right? For example, D is not a neighbor of A, so D cannot correct to A. But B and C are neighbor of A, so therefore they have to be on the same level. And that's what we call the level of the vertices. All right, the level of a vertex in a rooted tree is the length of the unit path from the root to its vertex. The height of the rooted tree is the maximum of the level of the vertices. All right. So you can see here, A is level at 0, and B, J, K, those are the neighbor of A, so that become level 1. So be very careful when you draw a graph on the exam. So make sure that they are at the same level, okay? Because they are the neighbor. So this is L1. So they have to be the same level of each other, right? So draw them carefully. Now CEFL will be level 2, right? So again, so they at the same locations, and that's level 3 right here, and that's level 4. Okay, be very careful with that. All right, so now we have level 4, so the height will be 4, because level 4 is the largest level of any vertex, so we have that as the height of the rooted tree that you see. Okay, so L1, L2, L3, and L4, and this A would be L0, that's the root. Okay, yeah, very straightforward. All right, so balanced embrate tree. So a rooted embrate tree of high H is balanced if all live at the level H or H minus 1. So what's the idea of leaf? Leaf is the one that doesn't have any child, right? Leaf is the one that doesn't have any children. So how many leaf do we have here? So we have, this is the leaf, this is a leaf, this is a leaf, this is a leaf, there's a leaf, that's a leaf, that's a leaf, right? So those are the leaf. So if the leaf located at the level, at the high H or H minus 1, then the tree is balanced. So you can see here the height is 4, so the leaf better be in the level of 4 or level 3. So that's good, that's good, 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 good. But this one is no good because it's way more than the condition for balanced rooted tree. So this graph is not balanced. Okay. So that's the idea. So which of these are balanced? So you can see here, 1, 2, 3, 4. So the high here is equal to 4. So high, h minus 1 is 3. So good, 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 good. So that's level 4. And this one here, good, 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 good. So those are the lift, right? So either level 4 or level 3. So yeah, T1 is balanced. All right, so again, 1, 2, 3, 4. So h equal to 4 again. So h minus 1 equal to 3. So good, good. That's 4, right? And good, good, good. But this one is no good. That's no good. So this T2 is not balanced. So this one here, 1, 2, 3. So high equal to 3, or h minus 1 equal to 2. So good, 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 and good. So this is good. So T1 and T3 are balanced, but T2 is not balanced because it have live at level 2, 3, and 4, which go against the definition of a balanced rooted tree. Make sense? Okay. So that's how we define the balance. All right. And a few property of a tree here. A tree with n vertices have n minus 1 edges. Okay. Yeah. So a tree with n vertices have n minus 1 vertex edges. Yeah, because if you have the same n vertex, then you would create a simple circus already. So that doesn't really define the tree, right? A full M-ray tree with I internal vertices has n equal to m times I plus 1 vertices, right? So n is a number of vertices. So you can see there, go back to calculate the number of vertices. So m times I. So I is the internal vertices. And then, so, okay, let's go back to this one here real quick, the M-ray tree. All right. All right, so T1 is a full binary tree. So it's 2 M-ray, right? So it's 2 ray. So it's at the number of vertices equal to m times I plus 1. All right, m is the number of rays. So we have 2 here. And how many internal vertices do we have? We have 1, 2, and 3. All right, so we get 2 times 3 plus 1, which give us 7 vertices. You can see here 1, 2, 3, 4, 5, 6, 7, right? 7 vertices. Okay, so that's demonstrate the theorem that we have there for full M-ray tree. Okay. All right, if an take a corollary one, so if an M-ray tree of high H has L leaf, then the high will be bigger than log base M of L. So you might wonder, what is that, right? So here we go. We call that the ceiling function. So the ceiling of X is the smallest integer greater than or equal to X. Okay, for example, you have the ceiling of 7.2 is equal to 8 because A is the smallest integer that is greater than or equal to X. Okay, so in this case, X equal to 7.2. So the ceiling of 7.2 is 8. It's an integer. Okay, so the high will be bigger than or equal to the ceiling of log base M of L. And if M bray is a full and balanced, then the height will exactly equal to log base M of Abel. All right. Okay, so that's the end of section 11.1. So when we come back, we take another section is 11.2.